Ever drive an EV? You'd know, because once you feel the thrill of electric, there's no going back. And the next generation of EVs by General Motors are an absolute joy to drive. Imagine an EV that can go from 0 to 60 in an estimated 3 seconds. And fully electric means you can feel good about feeling that thrill. This pleasure will be made possible by Ultium, a revolutionary new EV platform from GM that keeps the good times going. Discover the thrill that awaits at gm.com. Everybody in. Customer support can be chaotic, but it doesn't have to be. Intercom makes it easy to offer personal customer support at any scale. Take Intercom's help tool, Resolution Bot. It answers your common questions, reducing ticket volume for your customer support reps by up to 33%. Intercom also routes complex tickets to the right reps, giving your customers support that feels less like a maze and more like amazing. Go to intercom.com/support and find out why they're the #1 business messenger for customer support. Welcome to Tech Stuff, a production from iHeartRadio. Hey there and welcome to Tech Stuff. I'm your host, Jonathan Strickland. I'm an executive producer with iHeartRadio and I love all things tech. And over the history of this podcast, I have covered a lot of topics that were, at least at one time, little more than buzzwords to me. Cloud computing, machine learning, Internet of Things. A lot of these topics were either just not widely spoken about in mainstream society, or they were even just emerging within the tech world itself. This is where I have to remind all of you that I came into tech stuff as someone who loved technology, but who is not, in actuality, a technologist or an engineer or anything like that. And one of the terms that I started running into around 2014 or so, so it was after I had started this podcast, one of those terms was edge computing, or sometimes computing at the edge. And if you listened to yesterday's Smart Talks episode with Malcolm Gladwell, you heard a little bit about that in there. And now we're going to dive in whole hog. So today, I thought we'd talk a bit about what edge computing actually means and contrast it with other types of computing models. And we'll talk about how all of this is meant to work together in different ways and why it's even a thing in the first place and where edge computing is today and what we might think of it in the future. I thought that a good way to approach edge computing is really to start with some basic facts. There are certain things that we, as smarty pants human types, can do to speed up computer systems, to speed up the moment from where we put input into a system to when we get output from that system. We can create more efficient and powerful processors. For example, we can lean on parallel processing for some types of computer problems. Doesn't work for everything. Quantum computing similarly will speed up certain types of computer problems exponentially. We can design better software, and we can try to avoid Wirth's law. That's what the law that states that software tends to get slower at a rate that's faster than improvements in hardware. If we do combinations of all these sort of strategies, then the machines of tomorrow will, in theory, run software better than the machines of today. Again, assuming we don't just make even more bloated software that ends up canceling out our sick hardware gains. But there's one thing that we just cannot get around, and that is the top speed at which information can travel from one point to another. Even using a fiber optic cable and a clever optical system to deliver information, we are limited by the speed of light itself. Now that speed is, let me check my notes here, says wicked fast. When traveling through a vacuum, light zips along at 299,792,458 meters per second. Nothing goes faster. Thanks a lot, Einstein. What this means for us is that distance matters. Of course, until fairly recently, this wasn't the biggest concern for us because the way we did computing was pretty much always right up close and personal. So let's talk about that for a second. All right, so to begin with, We have computers that we physically access in some way in order to carry out a program. So in the very early days, people programmed computers by physically plugging in different cables into different sockets and throwing switches and, I don't know, waiting for lightning to strike or something. Okay, ignore that last bit. The process was tedious, it was complicated, it was easy to gum up. The speed of the computer was limited both by its own method of processing information, as well as the speed at which human operators could operate it. But once the computer actually finished the calculations, delivering them was pretty fast. I mean, sometimes delivering meant printing out a sheet of paper, or making little lights on a panel light up a specific way, and then the humans would have to consult a guide to figure out what that all meant. But if the computer had had a display, it would be able to throw up the answer as soon as it got there with zero delay. Flash forward a few decades, and we then had computers that had simplified input and output devices. You had your keyboards, you had your monitors and whatnot. Now programming a computer was far less convoluted, though as programming languages evolved, it could still be fairly easy for a human to gum things up with a careless error or a miscalculation or typo. Again, most of the time we were talking about people being all right up on the computer, and so there was really no delay between the machine arriving at the end point of a computational process and then delivering the result to the person who was using the computer. The information wasn't really traveling anywhere, it was just there. Then we get ARPA, the Advanced Research Projects Agency. It's the predecessor to DARPA. One of the projects ARPA tackled was to find a way to network different types of computers together. This was a big challenge for several reasons, but one of them was that different computers ran on very different processes, and well, we'll call them operating systems, but that's really being a bit generous. But the point is that the computers from different manufacturers, effectively they spoke different languages, and they could not directly communicate with one another in any easy way. Boiled down, the computers spoke math, but it was kind of like wildly different dialects of math. So there needed to be some sort of common language that all computers would be able to convert their native speech into, and then translate incoming speech back into their native language. Now that's a super oversimplified way to say that very smart people built out the protocols that would allow for the transfer of information across networks. We would eventually get stuff like TCP/IP that would facilitate these connections. Now, computers could connect into their network and they would be able to send information to and receive information from other computers on that same network. And as other networks took shape, they could interconnect with that first network, and then we got the network of networks, or the internet. So I'm giving a really fast rundown of the history of the internet here. This is like from space levels of high-level view of the history of the internet. All right, now we're going to skip way ahead. Let's get up to the 1990s, where the general public became aware that there was this thing called the internet, and the development and deployment of the World Wide Web really helped that along considerably. Now, we had this information superhighway. Or if you prefer, we had a series of pipes that let information flow from one source to another. Using this vast network of machines, we could send messages to friends on the other side of the planet, or check in on a particular coffee pot at the computer lab in the University of Cambridge in England, even if we happened to be in Athens, Georgia at the time. This, by the way, was actually a thing that once existed, and yes, I did use a computer in the University of Georgia computer lab to check and see whether or not there was coffee in a coffee pot across the pond. Normally there wasn't, because I was often in there in the afternoon, and it was several hours later over in the UK, but you get the point. Now, the way that information actually travels across the internet is pretty fascinating. First, information travels in bunches of data called packets, and this was a brilliant move early on in the development of networking technology. When computers send data across the internet, they chop that data up into packets. And a packet has two different kinds of data in it. There's data that's all about control information. So in other words, this is the data that explains where the packet came from, where it's going to, how many other packets the receiving computer should get in order to make up the entire file, and where within that sequence this particular packet should go. So you can think of that information as sort of like being the information on the outside of an envelope that you would send through the mail. Then you've got the payload, or the data that relates to the file itself, the thing you are sending. The packets are kind of like puzzle pieces that get reassembled on the other side. I actually think of it a lot like the sequence of Mike TV in Willy Wonka and the Chocolate Factory, the Gene Wilder version, that is. The description they give for how Mike gets broken up into millions of tiny pieces and then flies through the air and gets reassembled on the other side is sort of like what happens with data packets. Sort of. Well, those packets, which tend to be pretty small, like 1,500 bytes is common, they can all travel different pathways in order to get to their intended destination. If you think of the internet as just a huge interconnected series of roads that allow you to get from point A to point B, but you can choose literally thousands of different routes in order to do so, that's what I mean. These packets can all travel different routes. This actually helps make information transfers more robust. I mean, that makes sense, right? Because if you were to send a really big file that could not be broken up, well, first of all, you'd have to have a connection that could handle that much data being sent all at once, and that connection would need the same throughput all the way to the destination, or you would have to divide up the information in some way. And if you did do that, if you broke it up into packets, but all those packets had to zip down the exact same pathway, and then something happened halfway through the transfer, like maybe a connection broke, maybe a server went offline, whatever it might be, the incoming file would be incomplete on the receiving end. So packet switching helps ensure that communication between two computers across different networks can actually happen. But as you can imagine, if the user's computer is in one part of the world and the destination computer is on the other end of a communication channel on the other side of the world, then there might be a bit of a delay between sending something and getting something back, because that's a lot of distance to travel, a lot of hops to make on the way. We'll talk about hops a bit later, and so you can encounter some latency. Now let's move ahead a little bit more, and we get to the early days of cloud computing. The most basic definition I've ever heard about cloud computing is that it's computing, but it's happening on someone else's computer, which is pretty accurate. And there are a lot of subcategories we could talk about, like cloud storage. That doesn't necessarily require any computing on the server side, but it does mean you're saving stuff to someone else's machine, or more likely saving stuff to someone else's several other machines for the sake of redundancy. Cloud computing is really useful because you're no longer worried about the device that the end user is relying upon to do heavy lifting. One of the really big frustrations of owning a computing device is that, well, Moore's Law is a thing. Basically, we interpret Moore's Law to mean that every 2 years or so, the new computer processors that are rolling out of clean rooms are about twice as powerful as the ones that came out 2 years earlier. So we see processor capabilities effectively doubling every 2 years. It's actually a little bit more nuanced than that interpretation, but I've done full episodes about Moore's Law in the past, so we'll just go with the overly simplified but widely accepted definition. This tendency means that computer capabilities are on a pretty incredible trajectory, but the flip side of that coin is that any computer you buy today has a limited shelf life, at least as far as running the most current software goes. Even in the early days of personal computers, the joke was that by the time you got your computer home from the store, it was already obsolete. And that joke wasn't that funny because it felt all too true. Well, cloud computing offloads the computational lift off of the end user device and puts it on a server farm somewhere in the world. If the company providing the service is a really big one, or it's piggybacking off of a really big company like Amazon, then it might distribute those servers in different geographic regions. Otherwise, it could be in a centralized data center somewhere. The server farm provides the number crunching, and it means that the end user's machine doesn't have to be that advanced in order to take advantage of some heavy-duty computing power. This is what enables devices like Chromebooks from Google. These are very lightweight computers, both in terms of physical weight and their native processing power. That's because Chromebooks rely heavily on cloud-based services, so a lot of the actual processing is happening on machines that could be hundreds of miles away. The Chromebook itself is kind of a conduit for computational services. It's doing some work, but not most of it. This is the same strategy that powers things like streaming game services, like Google Stadia or Microsoft's Xbox Game Pass. The games run on specialized hardware that can crank up the settings on demanding games and then deliver all of that over a streaming internet connection. So as long as you have a good connection to the internet, you can enjoy a gaming experience that would otherwise require you to have a souped-up gaming rig or console. But while this removes some of the burden from the end user, who might no longer need to go out and buy the best computer to run the latest software, because that gets pretty darn expensive, particularly if you're interested in gaming. A gaming rig can run thousands of dollars if you want something that's state-of-the-art. But it does bump up against that fundamental speed limit that we mentioned at the beginning of this podcast. When we come back, we'll talk about how edge computing fits into this strategy. But first, let's take a quick break.
It's crazy how much we have to pay for outdated, impersonal healthcare, and even crazier that we all just accept it. It's time to face facts. Healthcare is backwards. Luckily, there's Forward, a new approach to primary care that's surprisingly personal and refreshingly straightforward. Forward never makes you feel like just another patient. Backed by top-rated doctors and the latest tech, Forward gives you access to personalized care whenever you need it. Using in-depth genetic analysis and real-time blood work, Forward's top-rated doctors provide you with in-depth insights to better understand your genetics, mental, and physical health. They then create custom, easy-to-understand plans to help guide you to achieving long-term health. With Forward, you get unlimited in-person visits with your doctor and access to care anytime via the Forward app, all for one flat monthly fee. It's time to stop accepting backwards healthcare and start moving your health forward. Visit GoForward.com today to learn more. That's GoForward.com.
Customer support can be chaotic, but it doesn't have to be. Intercom makes it easy for businesses like yours to offer personal customer support at any scale. Take Intercom's help tool, Resolution Bot. It answers your common questions, reducing ticket volume for your support reps by up to 33%. For the types of questions only a human can handle, Intercom routes tickets to the right reps at the right time, giving your customers support that feels less like a maze and more like amazing. Intercom also integrates with over 260 apps like Jira, AirCall, and Stripe, making it easier for your support team to work together to meet your customer needs. With routine tickets handled, your team will go from "this again" to "this is more like it." Go to intercom.com/support and find out why they're the #1 business messenger for customer support. That's intercom.com/support. Ever drive an EV? You'd know, because once you feel the thrill of electric, there's no going back. And the next generation of EVs by General Motors are an absolute joy to drive. Imagine an EV that can go from 0 to 60 in an estimated 3 seconds. A lower center of gravity that handles like a dream, letting you hug corners for a tighter ride. And don't even get us started on available towing capacity. Yeah, towing in an EV. And what's that? A quieter driving experience. It's about time you listen to your favorite podcast the way we intended. So get ready to charge up and feel the thrill of the road. It's all made possible by Ultium, a revolutionary new EV platform from GM, built for power, flexibility, and range, ensuring you keep the good times going. Isn't it time for everyone to feel good about driving a vehicle they love? Discover the thrill that awaits at gm.com. Everybody in. I've got a couple of other things that I need to say about network computing, and then I promise we're going to get to edge computing. One thing is that the internet has made it possible to have the actual Internet of Things. Now, back when I first heard this term, it didn't seem to be much more than just a buzzword. It was a concept that sounded intriguing, but hadn't really begun to manifest in a way that was visible to the general public. But starting around the early 2010s, that began to change. And today, there are more than 30 billion IoT devices connecting to the internet, with experts estimating that the total number will be somewhere in the neighborhood of 35 billion by the end of this year, and it's just going to get bigger from there. And these devices are all across the spectrum when it comes to purpose and intended user base and what the outcome would be. You've got the consumer-facing stuff that a lot of us have encountered, everything from smart thermostats to home security systems to personal medical devices to athletic trackers, all that kind of stuff. Then you've got more specialized variations like lab technology for hospitals and research facilities. You've got municipal infrastructure components that are turning traffic lights into smart intersections and that kind of thing. The variety and scope of the Internet of Things is unbelievable. And many, if not most, of these devices are pretty light lifters when it comes to processing information. For most of them, their main job is to gather data in some way, whether that's through optics or other sensors, and then they send that data up through the internet where some other system, somewhere connected to the network, will process the information and then presumably will do something with that info. So the output might be a readout that's useful to an end user. Like it might be that you look at your phone and you're able to see input based upon the Internet of Things that are around you. Or it might send that information off to some other related system so that a result will show up somewhere else, maybe in a way that isn't even obvious to us. The traffic light example could be a version of that, right? You could have a city-wide system of connected smart traffic lights that could detect changes in traffic patterns and perhaps respond proactively in an effort to minimize congestion, for example. This is actually a really, really complicated problem. It's not something that's simple to solve, but it would be impossible to solve unless you had a sort of Internet of Things infrastructure to collect and process all that data. But the era of lightweight devices connected to the internet really brings into focus the limitations we face if we rely on centralized data centers. The further out you are from that data center, the more delay there's going to be as the devices in your area are trying to communicate back with that distant center. There's just no getting around that because even if we made a perfect conduit between the data center and the end device, we'd still be limited by the fact that light has a speed limit. And here's where edge computing finally really comes into play. Now, I should also mention that edge computing is one of those things that has a few different interpretations and definitions. What it is largely depends upon whom you are talking to about it. So you might get slightly different definitions, but there are some general features that I think are common across all definitions. So if we visualize a typical cloud computer network, we might think of a centralized data center that connects out to various endpoints. Edge computing is a practice in which a company locates servers at the edge of networks. In other words, you are creating servers that can do data processing, and you are putting them close to where the data is actually being gathered or generated, as in you're putting it physically close to them. So, for example, I live in the city of Atlanta, Georgia. Now let's say that Amazon's Web Services, which provides hosting services to thousands of different apps and processes, let's say that they were all located in the state of Washington. That's where Amazon has its prime headquarters. Well, that's about 2,635 miles away from me, or around 4,241 kilometers. So if I'm running an application that needs super fast response times, in other words, I need really low latency, then I'm probably going to have a bad experience because the data has to travel pretty far, and it's not necessarily going in anything like a straight line because that's not how data traveling on the internet works. It's likely having to go through multiple hops. So I mentioned hops earlier. A hop is when a data packet moves from one network segment to the next network segment. So you can think of it as like hopping from one router to the next in order to get to its final destination. And the more hops that there are between me and the server that's running the app I'm actually using, the more latency I'm going to experience, because the data has to travel more hops in order to get to the server that's doing all the number crunching. Then it has to do the same thing in order to return results to me. So I'm going to experience this as lag or latency. But if Amazon instead set up different regional server farms around the world and located edge servers at those spots, the edge servers could take over the immediate processing requirements. So let's say Amazon set up that kind of data center in Atlanta, where I live. Now, instead of my device, whatever it might be, connecting back to Amazon's home headquarters in Seattle, Washington, it's instead connecting to this much closer edge server in Atlanta. The edge server can carry out whatever the immediate function is that I'm trying to do. So maybe now the data traveling between me and the edge server is only going through 1 or 2 hops. Not only is it traveling a shorter physical distance, it is having to make fewer transitions from one machine, like a router, on the internet to the next than it would if it were to go all the way back to Seattle. And the reduction in hops is critical for reducing latency. Now, this doesn't mean that edge servers totally replace centralized data centers. Instead, they work in concert with those centralized data centers. Edge servers kind of act as a point of processing for quick response. But you might want to have deeper analytical work being done by your centralized server. This work isn't necessarily as time sensitive, and in fact, the results of that work might not return to the end user, like me, at all. It might be things like trend analysis, where you're looking at millions of different transactions over a course of months and months and then drawing conclusions from that data. Well, that's not as time sensitive. That's literally looking at changes over time. So that can be done in a big centralized data center. It doesn't need to be offloaded to servers that are geographically close to me. Let's take an actual example. Let's say I'm using an augmented reality headset that connects wirelessly to hotspots and cellular networks. So this is an actual headset that I'm wearing. I've got a battery pack for it, and it's communicating with the network. I'm walking through Atlanta, and I'm looking at various features, and the augmented headset is displaying information about the stuff I'm looking at, and I can see that information within my view. It's overlaid on top of my view of the world around me. The headset would likely be fitted with stuff like a GPS chip, accelerometers, a magnetometer for compass directions, a camera to identify what it is I'm looking at, a processor, and so on. The headset needs to relay data to servers to process this information, to interpret it, and then to return relevant information to my view. The reason you want to do this is because by offloading those computational requirements to another machine, you don't have to make the AR goggles weigh like 50 pounds and have big cooling systems attached and everything, because they don't have to do as heavy a lift in the computational department. But this has to happen really fast. Otherwise, I'm going to see information about what I had been looking at a few moments before, while I'm now looking at something else, which would be really disorienting. I might look at a historic building and I might wonder, I wonder what this building used to be. And then I happen to look away and I'm looking at a tree or something. And then I see that apparently that tree is actually the historic Wren's Nest, which was the home of the controversial author Joel Chandler Harris. And heck, I might just think that my headset detected that there's an actual wren's nest in the tree I'm looking at. It would be confusing. So for applications like streaming video games to players using a specialized device, edge computing is absolutely critical. Like AR and VR, latency will ruin your experience in gaming. There's nothing like playing a game and feeling that bit of lag between when you press a button and when something actually happens on screen. You don't want there to be a perceptible delay between hitting a jump button and having your little Italian plumber dude actually jump. You want that to feel seamless. And humans are pretty sensitive to delay. You would want there to be less than 100 milliseconds, or 100 thousandths of a second, but even that is a little long. The general consensus is that the goalpost is to have delays of less than 20 milliseconds, and that is fast enough so that our mushy brains don't really process any kind of delay. If you've ever used a VR application that has even a tiny bit of latency in it, you've probably felt a sort of unpleasant swimmy sensation that can frequently lead to a type of motion sickness. And it's because you're sensing that delay between when you turn your head and when your actual point of view within the virtual environment adjusts. And your brain says, hey, something is really wrong here. And then it sends a message to your stomach to go hog wild because somehow that's going to fix things. All right. My understanding of biology is admittedly a little limited here, but the important bit is that latency is bad, and we must do our best to eliminate it. AR, VR, and game streaming are all really obvious examples of technologies that rely on low latency response time, while also typically requiring a high data throughput communication channel. So, when you hear people talking about applications that require stuff like 5G connectivity and edge computing, AR, VR, video games, those are all typically part of the conversation. And before I go further, I should also clarify that I specifically mean high-frequency 5G connectivity. If you've listened to my episodes about 5G, you know that there are a few different flavors of that technology, all of which relate to the band of radio frequencies that are being used. The higher-end frequencies within 5G can carry an incredible amount of information all at once. These are bands of frequencies that provide data speeds that rival that of dedicated fiber optic lines. But these frequencies also don't travel very far, and they can't penetrate solid walls very well, so you quickly lose out on that high volume throughput if you move away from the transmission antenna or something comes between you and it. It's why a really robust high-speed 5G network would need a lot of towers to make it work. Anyway, the 5G would be the communication channel, while edge computing would provide the actual processing capabilities to return relevant information quickly. You can imagine how edge computing would be important for all sorts of applications, not just VR, AR, and video games. The Internet of Things depends pretty heavily on edge computing, as the end devices, like I said, tend to be pretty simple. A lot of IoT devices boil down to a sensor that detects some sort of dynamic element. A thermometer, for example, detecting changes in temperature. Then it has a means of sending that information off to somewhere else. And it's that somewhere else that ends up making meaning of the data that the sensors are actually gathering. So the end device is, at least in a way, in this particular instance, kind of stupid. It's just giving constant updates, and a processing center is actually making use of that information. However, there are also some IoT devices that actually do have some compute capacity built into them. There are machines that have processing units, kind of like CPUs on a computer, and they also have memory and the ability to do at least some data processing right at the point of data generation or data collection. So if you were to go out and purchase a brand new car, chances are that car would have somewhere in the neighborhood of 50 CPUs built into it in order to control various functions, all of these operating independently of each other. But it also means that with the elements of the network, these can become effectively edge devices. So you've got your edge servers and you've got your edge devices, which if they weren't connected to any other network, you would just call them computers. When we come back, we'll talk a bit more about edge computing and some of the positives and some of the challenges associated with it, and what we might expect to see develop in the near future. But first, let's take another quick break. Customer support can be chaotic, but it doesn't have to be. Intercom makes it easy for businesses like yours to offer personal customer support at any scale. Take Intercom's help tool, ResolutionBot. It answers your common questions, reducing ticket volume for your support reps by up to 33%. For the types of questions only a human can handle, Intercom routes tickets to the right reps at the right time, giving your customer support that feels less like a maze and more like amazing. Intercom also integrates with over 260 apps like Jira, AirCall, and Stripe, making it easier for your support team to work together to meet your customer needs. With routine tickets handled, your team will go from "this again" to "this is more like it." Go to intercom.com/support and find out why they're the #1 business messenger for customer support. That's intercom.com/support. As we all start venturing out to hotels, restaurants, and grocery stores again, I'm sure you're thinking, how clean is this place? The Ecolab Science Certified program was created to help answer that question. Ecolab uses a suite of science-based products and protocols to help deliver a higher level of cleanliness at the places you eat, stay, and shop. So when you see the Ecolab Science Certified seal on the door, you know it's a place committed to clean. Listen, you don't have to be rolled into an operating room to get a scientific clean. You can take a weekend trip. You can order bottomless mimosas. You can shop for game day snacks. Because the same scientific expertise that helps clean operating rooms now helps hotels, restaurants, and grocery stores too. Learn how Ecolab is using science to advance higher levels of cleanliness. Look for the Ecolab Science Certified seal where you eat, stay, and shop. Ever drive an EV? You'd know, because once you feel the thrill of electric, there's no going back. And the next generation of EVs by General Motors are an absolute joy to drive. Imagine an EV that can go from 0 to 60 in an estimated 3 seconds. A lower center of gravity that handles like a dream, letting you hug corners for a tighter ride. And don't even get us started on available towing capacity. Yeah, towing in an EV. And what's that? A quieter driving experience. It's about time you listen to your favorite podcast the way we intended. So get ready to charge up and feel the thrill of the road. It's all made possible by Ultium, a revolutionary new EV platform from GM, built for power, flexibility, and range, ensuring you keep the good times going. Isn't it time for everyone to feel good about driving a vehicle they love? Discover the thrill that awaits at gm.com. Everybody in. One thing I haven't talked about so far in this episode is containers. Not physical containers that you would find in the real world, but rather the concept of containers within the context of software development and deployment. Now, remember how I talked about how packet switching and how information travels across the internet and how data packets play a part? Well, in a kind of similar way, containers are standard units of software. So we're not just talking about data, we're actually talking about applications here. And a container is a way to put together everything that a specific piece of software needs in order for it to operate. That includes the system tools that it needs, the code of the app itself, any libraries the code has to draw upon in the process of executing the program, and so on. So essentially, you can think of containers as all the stuff this particular app needs in order to do whatever it is the app does. Now, the reason that containers are important is that they allow developers to move software to different operating environments easily. Let's say that you are developing an app, and you might first develop it on your own machine. But then you actually need to test the app out. You've built it up to a point where you can run some tests, get some people in there to check it out, go through all the features, make sure it works. So you want to deploy it to a test environment, a discrete environment in which the app can behave as if it were released to the wild. But here's the important part. You haven't actually released it out to the wild. So that gives you the opportunity to find any problems with it, vulnerabilities, anything that could be detrimental once it was released. You can do all that in a safe space. So you do that and you find out what works and what doesn't work. You go back, you make some changes, you deploy it again to the test environment, you test it again. Once it gets to the point that the app seems to be working the way you wanted, Then maybe you move it to a staging environment. And from there, it goes into production. And it becomes an app that end users can actually download and install on their devices and actually use. Well, containers make it easier to move this app from one environment to another, from laptop to test environment and back again, or test environment to staging environment to production, etc. And these environments can all have different elements from one another. And those differences could mean that code that works really well in one environment suddenly doesn't work at all or is doing really weird stuff in a different environment. But containers contain all the elements that the app needs to run properly, so that, at least in theory, the code should run the same way, regardless of whatever environment it is in, because all the requirements for the app are contained along with the code of the app itself. Now, I get that this is a little difficult to grok for some folks. I mean, it's tough for me, and I have covered it multiple times. But beyond containers, we have another term that frequently pops up when we talk about cloud computing and edge computing. And that term is the dreaded Kubernetes, which refers to a now open source platform for container management. So, in other words, this is kind of one step up from the containers themselves. This is a product that helps teams operationalize containers at scale, because it's one thing to move a container from a developer laptop to a testing environment. It's another thing to deploy software that is going to potentially millions of users. So from a software perspective, we could say that Kubernetes and containers are trying to do from a code approach what edge computing is trying to do from a hardware approach. But in reality, all this stuff kind of gets mixed up together. Containers make it easier from an operational standpoint to deploy apps to the edge, whether that's to edge devices, where you're more likely to use a simple container platform, or to edge servers, where you might be relying on the more robust Kubernetes platform. So these are all pieces of a puzzle that makes edge computing a viable strategy. Now, there's some other considerations that IT professionals have to make when it comes to edge computing. Distributing computing to the edge comes with challenges. For example, when you've got your own on-premises cloud computing data center, you have a lot of control when it comes to ensuring the safety of your equipment and the information that it holds. That spans physical safety. That means you can actually make sure that those facilities are protected, that unauthorized people cannot easily get physical access to machines, that you've got a properly cooled facility to deal with all the heat that those computers are giving off, that kind of thing. It also means that you have more control over cybersecurity, so you can make sure that protections are in place to keep things running smoothly. But moving out to the edge creates more opportunities for bad actors to find a way to attack a system. So creating an edge computing network that is easy to administer and orchestrate while also being secure is a pretty big hurdle. It may mean leaning heavily on other entities and trusting that they've got their act together. And as we've seen pretty recently, sometimes that it turns out that a trusted entity has been compromised, and then there can be fallout. I'm specifically thinking about the SolarWinds hack. Now, in that case, we weren't talking about edge computing, but I'm using it to illustrate a point. The interconnectedness of these systems and the fact that you might be talking about half a dozen companies that own parts of this network that are all involved in this edge computing enterprise means that you're asking a lot of organizations to trust one another. And if one of those organizations gets compromised, there's a danger that hackers could take advantage of those trusted relationships to gain access to the others. Now, related to the issue of security is privacy. When it comes to the Internet of Things, we're often talking about devices that are gathering data about us and our activities. Yes, we've also got devices that are sensing environments and not so much focused on people, but a lot of devices are either directly or indirectly keeping track of where people are, who they are, and what they're doing. Now, that data can be useful for a lot of good things, but it can obviously also be misused or outright abused. So there is an onus on companies to make sure they are good stewards of data and that they protect that information. And since this information is potentially moving between lots of different points, from, say, the endpoint in the environment or on a user, through the edge network, and potentially further up the chain to a cloud computing network, there are a lot of opportunities for vulnerabilities. Now, while we often associate vulnerabilities with hackers who are trying to find ways to exploit systems, a vulnerability could just as easily be a poorly protected web portal that is publishing what should otherwise be private data. We've seen this happen with companies where someone along the chain failed to take into account what was actually going on, and data that should have remained protected and private was somehow published publicly or semi-publicly. As we look at decentralized computer systems, we see a lot more points where this kind of thing could potentially happen, either with the raw data collected in the wild or then the processed data that comes out of the edge network. Either way, that's something else that IT professionals have to focus on. Reducing the number of times data needs to move from one part of the system to the other is potentially one solution toward providing better privacy and security. You're reducing the number of hops, you're reducing the number of vulnerabilities that could potentially exist. If all the computing can stay at the edge and nothing needs to, phone home to the centralized data center, there are fewer opportunities for something to go astray. Similarly, we will likely see lots of companies specialize in ways to manage the flow of data between devices on the edge of a network and big data centers. I think that's going to be a really big business that it's like enterprise to enterprise business. But what if you're not an IT professional? I mean, I'm not. So what if you're like me? It's not your job to worry about this kind of stuff. What does all this actually mean to you? Well, essentially, it means the gradual introduction of more lightweight technologies that have increasingly usefulness in our lives. Well, maybe usefulness is going a bit far. We'll be able to do a lot more stuff with different devices interacting with our environments and with ourselves. Not all of it might be useful. I mean, I often talk about augmented reality applications like I did earlier in this episode, where you use an app on a smartphone, or maybe you're lucky you've got a pair of AR goggles and you're able to visualize the world around you in different ways. I love this idea of going to the site of an old castle and looking at the ruins and then seeing a virtual reconstruction of what the castle looked like when it was in its heyday. That to me is like the gold standard of AR applications, which can, it tells you that I majored in medieval English literature when I was in college. But I also admit that the reality of AR means I'll probably see a lot more, let's call them frivolous uses of the technology, like walking through a grocery store and seeing characters in the front of cereal boxes seemingly come to life, inviting me to enjoy their sugary goodness. Or I might look at a movie poster and suddenly a trailer for that film begins to play inside my vision. A lot of the services that we use are monetized in various ways. And I mean, I'm not knocking it. That makes sense. No one wants to work for free. But that often means that while certain technologies might have incredible potential, we also have to wade through a lot of less lofty applications. But edge computing is going to make that sort of stuff possible. Without edge computing, we wouldn't have the responsiveness capable of generating those experiences in a timely fashion. So with edge computing, we're also going to see a lot of one of my old favorite words, convergence. The convergence of multiple disciplines of technology, creating new approaches toward various problems. You've got your communication channels supplied by technologies like a robust 5G rollout. You've got your computer technologies at the edge of the network. Behind that, you've got machine learning, artificial intelligence, autonomous management, taking over tasks, optimizing them, always striving toward constant improvement. It's a pretty cool way to look at the future. Even something as seemingly dull as supply chain management really could have big results to consumers down the road, literally and figuratively. Imagine that the price of some goods starts to come down because we've actually developed far more efficient approaches to producing and shipping that stuff. and thus it costs less to get it to market. And various companies are competing with one another, so they reduce the price to you. That's one benefit we could see through this kind of robust rollout of edge computing. However, we have to remember, one, this version of the future is not a guarantee. It's a possibility. It's also good to think about the larger effect that we see as a consequence of more computing systems, more IoT devices, more processing, because this ultimately means we have to consume more energy. We need more electricity to fuel all this stuff, which means we got to produce more electricity, which frequently means we also are going to have a big ecological impact as a result of all this progress, assuming that we're still relying heavily on fossil fuels for our generation of electricity. Nothing exists in a vacuum, except for all that light zipping around out in space. This is all interconnected. We have to train ourselves to think about big picture stuff to tackle problems in a way that aren't exacerbating different but very important problems. Now, I never said I had all the answers. Heck, I only have a couple of answers. For example, the capital of Iceland is Reykjavik. Doesn't really apply here, but that's my point. But yes, that's our overview of edge computing and the role it plays within networks and our experiences with technology. It is one of those things that continues to evolve. And like I said, this one's a pretty young one. Like, I think the earliest mentions I could find were somewhere around 2013. So not that old in terms of technologies that we have at our disposal. So I'll probably be doing multiple episodes about this further into the future as we see it evolve over time and different implementations take shape. I'm excited to see what will become a reality based on this technology. And of course, I am concerned about the impacts that the technology will have beyond just its direct application. But I think we can leave off here, and then we will come back with new episodes about other stuff. So if you have any suggestions about other stuff I can cover, preferably related to technology, I mean, if you want me to talk about Reykjavik, I'll do it. It's just not, I don't know how well it fits in with tech stuff, and my sponsors might get mad. But heck, I'm game if you are. Let me know what you would like me to talk about in future episodes. The best way to do that is to reach out on Twitter. The handle I use is TechStuffHSW, and I'll talk to you again really soon. Tech Stuff is an iHeartRadio production. For more podcasts from iHeartRadio, visit the iHeartRadio app, Apple Podcasts, or wherever you listen to your favorite shows.
With MailChimp, you get a whole lot more than a URL. You get an all-in-one marketing platform to help drive sales. That means you can connect your data to make more informed, smarter decisions. And you get powerful automation tools like our Customer Journey Builder to ensure you never miss an opportunity to turn shoppers into loyal customers. So if you're ready to integrate your marketing and boost sales, get started today at MailChimp.com/smartmarketing. MailChimp, built for growing businesses.
You may remember seeing something about the death of Danye Jones on your social media feed around the end of 2018.
Well, a Ferguson, Missouri activist found her son hanging from a tree, and police are ruling it a suicide, but the mother believes it was a lynching.
He was not suicidal.
I'm Ray Novoselsky. Starting only 6 weeks after Danye was found hanged by a bedsheet, my colleague John Duffy and I spent 2.5 years working with Danye's mother, Melissa, to follow the trail and find out what exactly happened to him.
The lead detective in the case, he was laughing.
From Double Asterisk, Now This, and iHeartRadio comes an unforgettable new investigative podcast series, After the Uprising. All episodes are available now. Listen today on the iHeartRadio app, Apple Podcasts, or wherever you find your podcasts.